Okay, so now we're done with electricity and magnetism. Moving on to Chapter 6. Chapter 6 covers just reflection and refraction, but we'll also see some history about how people have viewed light over the past several centuries. I'm beginning with that. In the 17th century, Newton had an idea that light was a particle, and so he had this particle theory of light. Newton actually did a lot of work with light, and this particle theory of light was based on the idea of reflection. And he treated particles, or he treated light like a stream of particles. He called these corpuscles. And the reason he did this is because he observed it in the law of reflection. So he observed the law of reflection, which is something that particles do. So if you have a reflective surface and you shine a beam of light onto that surface, that light will reflect off. The law of reflection says that the incident angle is equal to the reflected angle. That is the law of reflection, that these two angles are always equal. And that's true with light, that these two angles are always equal, but it's also true with particles. If you've ever played pool, you know that if you strike the side of the pool table at a certain angle, then it's going to bounce off at the same angle. And this has been known for a long time, that both light and particles do this. Now, Huygens, on the other hand, who was a contemporary of Newton, he had a wave theory of light. So he treated light like a wave. So he would treat it like a wave. And the reason is because of refraction. He observed the refraction of light. The refraction of light is if you have a medium and light comes into that medium, then it will bend in a particular way. And we'll see how this works with refraction, how when light moves into different mediums, it bends one way or the other. This is purely a wave phenomenon. You could observe this with physical waves, like waves on the water, for example. When they enter a different medium, that is maybe a different depth of water or a different temperature of water, where the wave travels a different speed, then it will move to one direction or the other. So if you're in a body of water and you have a wave progressing through that body of water, if you enter a portion of the water where the water is now changed, say, as I said, a different depth or different whatever, then that wave can actually change direction, right? Because the velocity of the wave actually changes when it enters this new medium. And that is very much a wave-like property. And he observed refraction. Refraction was known to exist as a property of light. And so he developed this wave theory of light. However, Huygens' idea wasn't accepted at the time. One, the reason it wasn't accepted was because waves need a medium. For example, sound, which was known to be a wave and is known today to be a wave, if you remove the medium, which is air, so if you sucked all the air out of the room that you're in right now, not only would you die, but there would be no sound in the room because it would not have a medium through which to travel. Or if you didn't have the ocean, there would be no ocean waves because there's no medium. Right? So waves need a medium. And it was known then that you could get light to travel through a chamber that had been evacuated, that had no medium inside of it. It may or may not have been known then that light travels in space where there is no material, or at least very, very little material. But nonetheless, it was known that waves need a medium, and light did not have a medium. So that was an obstacle. Also, waves could bend around obstacles. So for example, if you stand behind a door and you say something, the waves that you generate with your mouth, the sound waves, can bend around the door and can go to whoever's on the other side of the door if it's partially open. Right? Scientists at the time thought that this was not possible with light. And we'll see later where we actually do get light will bend around an obstacle in a way, and we'll deal with that in the next chapter, or actually 2 chapters from now. Okay, so these were genuine beefs with Huygens' principle. Also, it didn't help that Newton was a rock star, basically, of the 17th century, and Huygens was relatively unknown, or at least not as popular as Newton. And so Newton at the time won out, and light was deemed a particle for a lot of years, until the 19th century, when Thomas Young discovered interference in light. Remember, Newton thought that light was a particle because of the law of reflection, and now Thomas Young discovers interference in light, and this is exclusively a wave phenomenon, and people at the time knew this. Basically, what happens is if you have 2 waves that line up in this way, that is, the peak of one lines up with the trough of the other, they cancel one another out. Or if I get 2 waves that line up like this, we call this in phase. If these 2 add together, I get a wave that is bigger in amplitude. Right? So this was purely a wave phenomenon. So for a long time, Thomas Young thought that that light was a wave. Now, in 1905, Einstein came along, and he explained the photoelectric effect. And the photoelectric effect, that metal surfaces emit charges when exposed to light. If you have a piece of metal and you shine a light onto it, here's my flashlight. If I shine a light onto this piece of metal, then electrons from the metal will jump off. Okay? And it was found that if you increase the intensity of the light, then you should get electrons with a higher energy. But that was not the case. If you increase the intensity of the light, that is, you just have more of it, more of the same color of light, then the energy of the ejected electrons should be higher, but it's not. Okay? If you increase the frequency of the light, then it turns out that the ejected electrons do have a greater amount of energy. All right? And Einstein explained this idea by invoking a particle nature of light. He said that these light particles, which he called photons, that when you increase the frequency of them, that they had more energy. So each individual photon had more energy, and then that individual photon would liberate an electron from the metal surface, and depending upon the energy of that individual photon would tell you what was going to be the energy of the ejected electron. All right. We'll see this again when we come on in a couple of chapters when we deal with the wave nature of light. But here you need to know Newton thought it was a particle based on the law of reflection. Huygens thought it was a wave based on the law of refraction. Thomas Young came along and said, no, it's a wave again, and basically discarded everything that Newton had done. And they said, well, light's a wave. That's the end of the story for a lot of years. And then finally, in 1905, Albert Einstein, for which he won the Nobel Prize, described the photoelectric effect. Now, he didn't discover the photoelectric effect. Another scientist did that, but he described the photoelectric effect in terms of a particle-like nature of light. And then so Einstein proposed, no. It's neither a wave nor a particle. It's both. They have this wave-particle duality, and we'll talk about that later. I have a video. There are a number of other interesting characters in this development on the nature of light and our understanding of it, and you can watch that here. And we will pause here and pick back up here. Notice you have a number of questions. Oh, actually, let's see. So today we settled that light has a dual nature. Sometimes it acts as a wave, and sometimes it acts as a particle. I'm going to wait. We'll watch this video. Actually, no, we'll go and watch it now. So you can go and watch this video here, the Dr. Quantum video, where he talks about this as well. But we'll see this again later.